Welcome back, everyone. So, we are going to continue our discussion from the last class. Basically, in the last class, we discussed how to set up the equation of motion by using two methods. The first method used method of direct equilibrium, in which we basically used equilibrium conditions to set up the equation of motion. And then the second method used method which is called influence coefficient method. And we saw that using both methods, we can set up the equation of motion for a multi-degree of freedom system. So we are going to do some examples today and apply both method to actual problems and see how to actually utilize those methods to set up the equation of motion for a multi-degree of freedom system. In the last lecture, we discussed that if we have a multi-degree of freedom system, how to formulate the equation of motion of a multi-degree of freedom system. Okay, and we took the example of a shear type building in which we said that, okay, we took an example of a three-story shear type building in which we said that the building has 3 degrees of freedom represented by U1, U2 and U3, and it has masses basically lumped at each level, and the story stiffness is represented by K2, K1, K2 and K3. Okay, and we found out the equation of motion of this three-story building subject to external load. Okay, so these external loads were basically P3, P2, P1 applied at the respective stories. Okay, and the equation of motion that we got was of this form. Okay, M1 0 0 0, M2 0 and 0 0, M3. So we got this mass matrix, and then if there's also damper at each between each story, okay, then that can also be formulated in this equation of motion, and we can write this as C1 plus C2 0 0, sorry, C1 plus C2 and then minus C2 0 minus C2 C2 plus C3 0 0 minus C3, there should be C3 here, no, minus C3 here, and then this is C3. Okay, with the velocities, and then we had the stiffness terms which took the same form as the damping term. So I can write this as K2 plus K3 minus K3 0 minus K3 K3. Okay, and then U1 U2 U3, the displacement vector, and this is equal to the applied load vector. So in general, the equation of motion of a multi-degree of freedom system can be written as, okay, inertial force vector plus the damping force vector plus the internal force or the stiffness force vector equal to the applied force vector, and this is basically the extension of the equation that we had used for a single degree of freedom system. And of course, in this case, for the case that we have considered here, can be written as mass times acceleration. Sorry, there is an acceleration terms here. Okay, so acceleration vector plus damping would be damping matrix times velocity vector, and then there is internal force, that is stiffness matrix times the displacement vector, and this is the applied force vector. Okay, so this is the general form of the equation of motion, and we also talked about that this equation of motion can be derived using two methods. Okay, in the first method we can simply consider the free body diagram of the system that is shown here. So either we can cut this system at these three locations and write down the three equation of motion corresponding to each masses. Okay, and that is called the direct equilibrium method, in which we are going to directly write down the equation of motion and then formulate these matrices and vectors here. In the second method, we talked about the influence coefficient method. Okay, and in the influence coefficient method, we said that I'm going to formulate stiffness matrix, okay, by considering the unit displacement at any degree of freedom and then finding out the forces required to have that unit displacement maintained at that particular degree of freedom and zero displacement everywhere. Okay, and the forces that we get, basically those forces are the column vector, okay, column vector of the stiffness matrix, and these coefficients are called the influence coefficient, and we are going to repeat that for each degree of freedom to find out the whole stiffness matrix. Okay, so we said that Aij is nothing but force at degree of freedom I, okay, due to unit displacement at degree of freedom j. Okay, and the same concept can also be extended for the damping matrix, in which the same thing. Okay, so let us say C11, C21, Cn1, and the damping matrix can be obtained assuming Cij would be the force at DOF I due to unit velocity at degree of freedom j. Okay, similarly the mass matrix can also be found out like that. Okay, and Mij is basically force at DOF I due to unit acceleration at DOF j. Okay, so in these cases, what do? We first consider unit displacement at any degree of freedom, let us say j, and zero displacement everywhere, and we find out forces that need to be applied at each degree of freedom to maintain that state of deformation. Okay, and that can be done using the static analysis. Okay, so this is considered in the stiffness component of the structure. This is considered in the damping component. Okay, and this is considered in the mass component. Okay, so this component basically means that in this, the stiffness component, we only consider the bare frame. In the damping component, we only consider the dampers, and in the mass component, we only consider the masses in the system without the frame or the damper. Okay, and we consider the representation of a multi-degree of freedom system can be written as a sum of three individual components: the stiffness component, damping component, and the mass component. So using this method as well, we can formulate our equation of motion like this. Okay, so in today's class, what we are going to basically do, employ both these method, direct equilibrium method and the influence coefficient method, to find out the equation of motion of different type of systems. Okay, so let us do the first example. Okay, so in first example, basically what do? I'm going to consider the same example that we did last class. So I have a continuous bar, a rigid bar, okay, and the mass is distributed over the length L. Okay, and force vectors Pt and p theta are being applied at the center of this rigid bar. Okay, and the degrees of freedom are u1 and u2. Okay, so basically, and these springs have stiffnesses k1 and k2. So the equation of motion need to be found out using both method, first the direct equilibrium method and then the influence coefficient method. Okay, so let us first do the direct equilibrium method. So as we know, a rigid bar in 2 dimension, okay, can be represented as 2 degrees of freedom. So let us say initially the bar was here, but at any time t, okay, the degree of freedom u1 and u2. Okay, so this is u1 here and this is u2 here. So this bar in 2 dimension can rotate or can translate. Okay, so it can do both motion, and to represent the motion we need 2 degree of freedom to represent its displaced position with respect to the initial equilibrium position. Okay, now this is the deformed position, so we need to draw the free body diagram, okay, of this bar in a deformed position. Okay, so let us do that. Now as I know, as you know, you have a spring here, so when it is deformed by u1, force that would be applied here would be k1 u1, and then there is another force which is basically k2 u2. Now I'm going to apply two pseudo quantities here. Okay, so because this bar can translate and can rotate, I'm going to apply the pseudo translational inertial force and the pseudo rotational moment, okay, against the direction of translation and rotation. So it is translating in this direction. Okay, so let me just so it will have, the bar would have mass times acceleration at this point. Now acceleration at that point can be written as acceleration at the end 1 and acceleration at the end 2 divided by 2. Okay, because it is at the middle point. So this is the pseudo translational force. Now it is rotating anti-clockwise, so a clockwise pseudo moment would be applied to it, and that would be the moment about its center of mass, let us call this ICM, times the rotational acceleration, which I can write as u2 minus u1 divided by L. Okay, basically this is the angle here. Okay, so the angle theta here, okay, for this is basically, you consider u2 minus u1 divided by L. Okay, and the rotational acceleration would be just the double differentiation of that quantity right there. Okay, remember that there are two forces as well here, so you have pt and p theta. Okay, so utilizing that, let us write down the equation of motion. Now to write down the equation of motion, what I'm going to do, I'm going to first write down, let us consider this as end A and end B, summation of moment about point B equal to 0. What that would give me directly, the equation, let us write it down here. Okay, so I will have Im, okay, times u2 minus u1 divided by L, and this is basically clockwise. Then I have k1 u1 times L, which is anti-clockwise. Okay, and then I have m u1 plus u2 divided by 2 times L by 2. Okay, and this quantity is basically anti-clockwise, and then I have force pt, which is creating clockwise moment, so pt times L by 2 and then a anti-clockwise moment p theta, okay, and that is equal to 0. Okay, so with that, let me just rearrange the terms here. Okay, so we'll have mass times, remember Im, the moment of inertia of this would be bar ml square by 12. Okay, now I'm going to substitute that in the equation of motion over there. So let us do that here. Ml square by 12 times u2 minus u1 divided by L here. Okay, and then again I have this term here, u1 plus u2 acceleration divided by 2 times L, and this becomes 4 here. And this quantity here, k1 u1 times L plus pt L by 2 minus p theta. Okay, so let us further simplify this one. Okay, so this we can write it as m by 3, okay, u1 plus oh, m by 6 times u2, okay, and this plus k1 u1 here, and this is equal to pt by 2 minus p theta by L. Okay, similarly, what I'm going to do here, write down the equation of motion summation of ma equal to 0. Okay, and let us write that down. So when I do that, it will have Im, which is basically again Im times u2 minus u1 divided by L plus m times u1 plus u2 divided by 2 times L by 2. Okay, both clockwise. All right, about point A. Then I have k2 u2, which is again clockwise times L, and then we have p theta, which is anti-clockwise, and pt, which is also creating anti-clockwise moment. So if I take it to the right hand sign of the equality, I would get that as pt plus, okay, so let me just write down pt times L by 2 plus p theta here. Okay, so this I can write down as, again I can simplify this as m by 6 u1 plus m by 3 u2 plus k2 times u2, and that is equal to pt by 2 plus p theta by L. Okay, so equation 1 and equation 2 can be combined together in the matrix form and written as m by 3 times m by 6, again m by 6 times m by 3, and then the acceleration vector here. Okay, and then I have the force vector k1 0 and 0 k2, and then the displacement vector, and that is equal to the force vector, which comes out to be pt by 2 minus p theta by L. Let me write it again, and then pt by 2 plus p theta by L. So There's some important point to note here. If you look at it, this is a distributed mass bar. Okay, so the mass is distributed throughout the length. And the degrees of freedom are actually defined at the ends of this bar. Okay, just above K1 and K2. So if you look at it, okay, we get the stiffness matrix as diagonal matrix. However, if you look at this mass matrix, it's a non-diagonal matrix. Okay, and the forces also, you do not directly get the force Pt and P theta. So, and this is basically the implication of how you define your degrees of freedom. Okay, because the degrees of freedom in this case were directly above K1 and K2, okay, which represents the deformation in the two springs, I get a diagonal stiffness matrix. But if you look at the displacement here, it does not correspond to a single lumped mass. Okay, it's a distributed mass and it does not correspond to the direction of the applied forces, which are forces and moment, which are Pt and P theta. That's why again we don't get directly the diagonal mass matrix or a single force vector that comprises of directly the Pt and P theta. Okay, so this is the equation that we obtained using the direct equilibrium method. Let us obtain the same equation. Okay, or let us see what do we obtain if you utilize the influence coefficient method. Okay, influence coefficient method. Now, in the influence coefficient method, let us start with the formulation of the stiffness matrix. Okay, and if you remember, to get the stiffness matrix, first we are going to apply the unit displacement at each degree of freedom with zero displacement at the other degrees of freedom and find out the columns of the stiffness vector. Okay, so let us do that. So in the first case, we are considering u1 equal to 1 and u2 equal to 0. Okay, so basically the deflected shape would look like something like this. So this is my bar here. It has u1 equal to 1 and u2 equal to 0. Okay, now to maintain this shape, we would have to apply forces, which would be the influence coefficient for the stiffness matrix. So those forces would be at the degree freedom 1, the force due to unit displacement at degree of freedom 1, and force at degree of freedom 2 due to unit displacement at degree of freedom 1. So these would give me K1 and K11 and K221. Okay, and remember in this case we have subject to this deformation. Okay, K11 and K22, we only consider the stiffness components. Okay, not the mass component or the applied force or anything. Okay, now subject to this displacement, we know that we have two springs as well, right? Because we still need to consider the stiffness component. So these forces need to be applied, but with this displacement, we know that there will be a downward force at K1, which would be K1 times the deformation in that spring, which is 1. And then here K2 times the deformation in that spring, which is 0. Okay, and again we can solve this. Okay, so let us write down. If I write down the equilibrium summation mb equal to 0, I can directly get as K11 times L is equal to K1 times 1, okay, and times L. This is equal to 0. So K11 is nothing but K1. Similarly, if I consider summation m equal to 0, I would get as K21 times L minus, there is no moment created by the force K2 because it's 0. Okay, equal to 0. So K2 equal to 0. Okay, so we've got the first column of our stiffness vector, which is K1 0. I still don't know what this is. Second column, to get that, let us say u1 equal to 0 and u2 equal to 1. So in the second case, I will have the deformation state, which is something similar to this one. So u1 equal to 0, u2 equal to 1. I will have to apply the forces which are force at degree of freedom 1 due to unit displacement to degree of freedom 2, force at degree of freedom 2 due to unit displacement degree of freedom 2, and subject to this deformation state, it would have the spring forces which are 0 at this point and k2 times 1 at this point. So again, utilizing similarly the equilibrium of equation, I can get as k12 as 0 and k22 as 1, k2. Okay, so I have obtained k0, 0, 0, k2, and this is my stiffness matrix. Okay, so although I have demonstrated for 2 degree of freedom, we can extend it for any degrees of freedom. Okay, now let us come down to finding out the mass matrix. Now for the mass matrix, we are going to repeat the similar kind of procedure, except now we are going to doing the same thing for the acceleration, not the displacement. So in the first case, okay, just so in the first case, I'm going to assume unit acceleration at point A and then 0 acceleration at the second degree of freedom system. So in this case, I have unit acceleration at this point and then 0 acceleration at this point. And remember, we only consider mass in this one. There is no spring or anything in this system. Okay, so to get the mass matrix, we only consider the mass component of the system. So unit acceleration 1, acceleration 0. So it would be varying somewhere linearly between these two acceleration. Now, because the mass is distributed, the inertial force on this bar, okay, if you consider x to represent the displacement from the or the position from the rightmost end, then at any point the acceleration is basically x by L times u1 double dot, which is 1. So the acceleration ux is basically x by L. Okay, now the inertial force would simply be, all right, whatever the mass, okay, x, now mass x is basically m divided by L. Okay, so the inertial force at any same distance would be Fix equal to m by L, mx times the acceleration at that point, which would be x. So mx by L square. Okay, and now we are going to write down the equilibrium equation for this one. So what will happen, I have inertial forces which are distributed like this, and to maintain the state of acceleration, I need to apply force m1 due to unit acceleration at 1, and then force at degree of freedom 2 due to unit acceleration at 1. Okay, so in this case, if I consider summation mb equal to 0, then I can write it as m11 times L is basically equal to the net effective inertial force, which would be in this case half times L times m divided by, so the net resultant force in this case, if you consider for this one, would be m divided by L. Okay, now this force would be acting at distance which is 2L by 3. So that need to be mentioned. Or you could just simply write it as, if you take the integration of it, the total moment would be basically m by L times x by L times x 0 to L. Okay, and that would give you m by 3. Okay, or that is not ml by 3, let us say it is ml by 3. And in this case, if you look at it, you get the same quantity here. So m11 is basically m by 3. Okay, similarly, if I consider summation ma equal to 0, then you will get m21 times L is equal to the same quantity, but now from the left hand side it is at distance L by 3. So here you get m21 as m by 6. So we have got the first column m by 3 and m by 6. We still need to get the second column here. Okay, so we are going to follow the same procedure and we are going to apply 1 equal to 0 and in this case u2 equal to 1. So now basically consider inertial forces would be acting opposite to the direction of acceleration, and I need to apply force at degree of freedom 1 due to unit displacement degree of freedom 2, force at degree of freedom 2 due to unit displacement at degree of freedom 2. Okay, and then the force that we'll have here, remember again this is u2 equal to 1 and the inertial force at any distance is same quantity m by L times the acceleration x by L. Okay, so I can employ the same equilibrium equation. In this case, you can get as m21, okay, or not m21, m12 is m by 6 and m22 is m by 3. Okay, so this is m by 3, m by 6, m by 6, m by 3. All right, so mass matrix is also obtained as this m by 3, m by 6, and m by 6 and m by 3. So we have obtained mass matrix, we obtained the stiffness matrix. One more quantity that need to be obtained is the force vector. Now if you look at it, okay, I have this bar here in which the applied forces Pt and P theta are actually not applied the degree of freedom u1 and u2. Okay, so I need to find out the equivalent force system for this so that Pt and P theta can be basically decomposed or it can be rewritten so that along the degrees of freedom u1 and u2. Now let us say the forces P1 and P2, okay, these two forces are equivalent. These are two systems are same systems. Okay, so in order to achieve the same thing, okay, what we are going to do, again we are going to write down the equation of motion, okay, for this system. Okay, so let us go ahead and write down the equation of motion. Okay, so in this case, let me first let me just first write down P1 plus P2 is equal to Pt. Okay, because if you consider same thing, okay, so at this point the net resultant force at this point is P1 plus P2. The net resultant moment at this point is basically P2 minus P1 divided by L by 2. Okay, and this is the net moment in the anti-clockwise direction at this point, and that is equal to theta. So we can solve this and we can find out P1 as Pt by 2 minus P theta by L and P2 as Pt by 2 plus P theta by L. Okay, and this simplification we only did because our degrees of freedom or the applied forces were not applied at the degrees of freedom that we had considered for this problem. So now we can write down the equation of motion as m by 3, m by 6, m by 6, m by 3, and the acceleration vector. Okay, then the stiffness vector k1, 0, 0, k2, u1, u2, and then the force vector. Okay, and we can compare this to the direct equilibrium method and see we have obtained the same equation of motion. Okay, so which method to employ in what kind of problem you would only learn through looking at the problem and doing or practicing more problem. Okay, so sometimes one method is usually easier to apply for a specific type of problem compared to other method, and there is no fixed rule as such. Okay, so that you would only need to apply, but remember that it doesn't matter which method you employ, as long as you are doing it correctly, in the end you should get the same answer. Okay, although you might find one method to be a little bit difficult than the other method for some type of problem. Okay, all right. So after this, what we are going to do, or for this problem, let us say instead of considering the degree of freedom along the two spring, okay, had we considered the degree of freedom as the ut, which represents the translational motion, and u theta, which represents the rotational motion, so that the deformed position can again be this as ut and this as u theta. Okay, and the rest of the parameters remain same, k1, k2. Okay, okay. So in this case, again I have pt and p theta like that. So in this case, you can go ahead and you can find out the equation of motion. Okay, you would get equation of motion which is little bit different, and I'm not going to solve this system. I leave it for you to solve the equation of motion, and let me just write down the final equation of motion. Okay, so we get as m0 0 ml square by 12 times ut and u theta, and then k1 plus k2 minus k1 times L by 4, then k2 minus k1 L by 4, and then k1 plus k2 L square by 4, and u1 u2, and this is equal to pt times p theta. Now notice an important difference compared to the last equation that we had written here. In this case, we are defining the degrees of freedom ut and u theta, which are along the center of mass and the center of rotation, or we can say that it represents the degrees of freedom along the mass, translational rotation, and the rotational motion. So that's why we again get the diagonal matrix in which we have the mass term and we have the moment of inertia about the center of mass. Okay, however, because now the degrees of freedom are not defined along the springs, we get non-diagonal matrix for the spring, and the force vector, because the degrees of freedom are along the force vector, now we directly get as pt and p theta. Okay, so we get two different equation, although they are not exactly different. I'll just will come back to that. Okay, depending upon the equation or the degrees of freedom that we have defined. Okay, now you might see a different formulation of equation of motion, but we'll see in the next chapter. A dynamic system is basically defined through its modes, shapes, and frequencies, which are called modal properties. So even if you see that these equations are somewhat okay in a different form, basically they represent the same system, because through some mathematical manipulation this can be transformed to this, or this can be transformed to this. Okay, and we use something, a matrix that is called a transformation matrix, to do that. And let us quickly see how do we do that. If we consider a system, okay, equivalent system. So let me just take example of this one. Remember, we had a system, so in the deformed position it looks like this. Now first time what we did, okay, we consider u1 and u2, Okay, which were the displacement at these two locations to represent the deformed shape. In the second case, we considered ut and u theta to represent the displaced position. Okay, now if we consider here, okay, can I say my u1 is nothing but ut minus u theta L by 2, and u2 is ut plus u theta L by 2. Okay, so that I can write it in a vector form. u1 u theta u1 u2 is actually equal to 1 minus L by 2 and then 1 L plus L by 2 times ut and u theta. Okay, this matrix here is called the transformation matrix. We're going to represent it A, and we'll see that these two systems are basically equivalent, and if we need to transform a system from ut to u theta, okay, let us say in the second case, okay, so first case, let us say the mass matrix is M, the stiffness matrix is K, and the displacement vector is U. Okay, in the second case, let us say mass matrix is M dash, stiffness matrix is K dash, the displacement vector is U dash. And if I write it like this, so basically the equation is here, U is equal to transformation matrix A times U dash. Okay, I can substitute this formulation so that you will look at it here, and your stiffness would basically become K dash equal to transformation matrix transpose times this K times transformation matrix, and M dash is transformation matrix transpose times the initial mass matrix times the transformation matrix. Okay, so these are actually related, these two systems, and they represent the same system, and we can switch from one system to other system by utilizing these equations. Okay, and if you have taken a course in structural mechanics, you would have learned about this transformation matrices. Okay, all right, once this is clear, remember we have been writing down our equation of motion as mass matrix times u, damping matrix times, acceleration vector times velocity vector, and then stiffness matrix then the displacement vector as p. Now this is for any load vector p. Now if we consider earthquake ground excitation of multi-degree of freedom system, so earthquake loads, okay, so for this type basically earthquake loads, what we are doing, let us consider the lumped mass representation of the 3-story shear type building. So in this case, I will have certain displacement like due to the ground excitation, let us call this UGT, and let us represent the ground acceleration as UG, and then the relative displacement UT. Okay, now at any degree of freedom, let us say, okay, so let us say this is the ith degree or jth degree of freedom. Okay, the total displacement, let us say this is J, the total displacement, okay, at the jth degree of freedom would be the ground displacement plus the relative displacement, okay, of the jth degree of freedom. All right, okay, now if we write that, we can also write down our velocity by differentiating it once and the acceleration by differentiating it twice, and then substitute it in this equation of motion. Okay, keeping in mind this acceleration is actually the total acceleration, and this velocity and displacement are actually relative velocity and relative displacement. Okay, so let me just write down that this is equal to, okay, so in terms of vector representation, this can be written as let us say vector u. I'm writing down for acceleration. Ut is equal to ug, which is basically vector of the same quantity. Okay, ug throughout the in a column, and then I have ugt, which I can write as u1, u2, u3. So this would be the relative displacement vector. Okay, so because I have the same quantity UGT, I can write this as unit vector. It's not a unit matrix. Okay, it's not a, so just keep in mind this is a unit vector times UG double dot T. Okay, plus U of T. Now in this case, if I substitute it, I would get the final expression as this times the displacement, the relative acceleration vector. Okay, U plus relative velocity and then relative displacement. This is equal to minus m times 1 times basically the quantity ugt here. And this is my effective force vector for a seismic excitation of a multi-degree of freedom system. Okay, so I'm going to write my P effective as minus m, this one, and then ugt. Okay, all right. Now, one thing to notice here, that in this case, my degrees of freedom were in the same direction, okay, as the ground excitation. Now, it might happen that my degrees of freedom might not be defined in the same direction as the ground excitation. In that case, this quantity that I get here, 1, or the unity vector, it might not be actually unity. And then in that case, we represent it as a influence vector, okay, which is denoted as L. Okay, and which basically represents the relationship between the direction of the ground motion and the direction or the degrees of freedom. Okay, and I'll give you some examples to show that what I basically mean by that. Okay, so let us say, okay, I have, in this case, we had a building. Okay, so in that building, my ground excitation UGT is along the degrees of freedom. Okay, so that I could write this as 1. The influence vector is 1. However, in the second case, let us say we have something like this, where the masses are actually lumped and the degrees of freedom are defined it like this: u1 in this direction, okay, u2 in this direction, and then u3 in this direction. Okay, so in this case, let us say this is ug. So to get the influence vector, okay, let me first write down my total acceleration vector, okay, as, or first let us say for any jth degree of freedom, uj t, the total displacement as the relative displacement plus the ground displacement. And if we write it in terms of vector, it would be total displacement vector as a relative displacement plus the vector, okay, the ground vector ug. Now, if my degrees of freedom are not along the ground excitation, then this we write it as ut plus some vector L times ugt. Okay, not acceleration, we are still considering the displacement here. Okay, sorry, Let me write it again here. Now, what do we do to find out this influence vector? We apply a unit ground displacement in whichever direction the ground excitation is applied. So you apply a unit value of the ground displacement, and then you look at it for that unit ground displacement, what happens to the displacement along each degree of freedom. Okay, for example, in this case that we have here, if I apply ug equal to 1, okay, and we are doing it statically, okay, so this is just finding out the relationship. So if I apply ug equal to 1, okay, all of these degree of freedom will move by 1, correct? So that's why my L becomes 1 1 1. However, in this case, if I apply ground displacement equal to 1, u1 moves by 1, u2 moves by 1, u3 basically is 0, because there is no vertical, there is no displacement in the vertical direction due to the unit ground movement of 1. So in this case, basically my L becomes 1 1 and 0. Okay, so that my influence vector can be written as 1 1 0. Similarly, let us say for the same thing, I have something like this. Instead of I have three masses here, and instead of a translational ground motion, let us say I have a rotational ground motion. So theta g is there. So in this case also, what do we need to do? Just apply a unit rotation of theta g equal to 1, and then see along each degree of freedom what is the displacement corresponding to this one. So this would be, if this height is, let us say h1, this would be 1 times, remember if this angle is 1, this is 90 degree, okay, then this angle would also be unity. So this would be h1 times 1 along this degree of freedom. If u2 and u3 are this would be whatever the height that we consider, let us say h2 times 1, okay, in this direction, and this would be whatever the length of this is, let us say this is h3 here, okay. If this is rigid, this connection here, if this rotates by theta, this would also rotate by theta, and it would come down by the length times this angle. So that would be h3 times 1. So the influence vector here would be h1, h2 and h3. Okay, and once we get the influence vector, we can find out the effective force vector as minus m times the influence vector, okay, times the ground acceleration. Okay, if it's a translational ground acceleration, if it's a rotational ground acceleration, then this would be L times theta g t. Okay, and we can write down our equation of motion as same as mu plus c of u plus k of u, and this is equal to the p effective. Okay, so we have seen that how to set up the equation of motion for a general load vector and also for the seismic excitation by obtaining the influence vector. Okay, and we learned basically two type of method to set up the equation of motion. The first one was the direct equilibrium method, and the second was the influence coefficient method. Okay, so with this we would like to conclude this chapter. Okay, in the next chapter we are going to study how to get the modal properties of a multi-degree of freedom system. Okay.